Hello everyone, I'm J Wildberger. In this lecture, we're going to look at trig identities and how they are simplified, sometimes quite dramatically, by using the exponential function. So last time we had the following important identities. We saw that first of all, let's do that a little bit down here. First of all, the exponential function, the complex exponential function, is defined by e to the I theta is cos theta plus I sine theta. And its complex conjugate, e to the minus I theta, is cosine theta minus I sine theta. And from those, very quickly we were able to deduce that cosine theta expressed in terms of the complex exponentials is e to the I theta plus e to the minus I theta all over 2, and that sine theta is equal to e to the I theta minus e to the minus I theta all on 2. Fabulous. All right. So those are sort of fundamental relations that we're going to be looking at today. So we want to look at some trig identities. And what kinds of things do we have in mind? Well, they're very simple ones that are actually quite useful. They're important, for example, in calculus when you want to integrate. Often having some nice trig identities makes things a lot easier. So what kind of things are we talking about? Well, for example, you'll all know that cos 2 theta is cos squared theta minus sine squared theta. And we can rewrite that, if we want, as 2 cos squared theta minus 1. Or maybe sine 2 theta equals 2 sine theta cos theta. That's a kind of useful kind of expression. But what about, for example, cosine of 3 theta? Okay, that's maybe a little bit less familiar. So that turns out to be 4 cos cubed theta minus 3 cos theta. And we might ask, how might we be able to establish and actually discover such identities? It's a natural question. So let's have a look at sine 2 theta, say these first two here. So from the exponential is de Moivre's theorem. Okay, so de Moivre's theorem, I'll remind you, is cos theta plus I sine theta to the n equals cosine n theta plus I sine n theta. Or in exponential form, e to the I theta to the n equals just e to the I n theta. And that's a particularly nice way of thinking about it because it's just the usual kind of index law for the complex exponential. Okay, so this suggests how to obtain some identities like this. If we let n equals 2, for example, then we would get that cos theta plus I sine theta squared should be cos 2 theta plus I sine 2 theta. But this thing here, this cos theta plus I sine theta squared, that we can expand by the binomial coefficient. So it's the square of the first term plus the square of the last term. Maybe I'll put twice the product first. Plus 2 cos theta times I sine theta. Those are the products of the two terms. And then plus I sine theta squared. Okay, so if we simplify that a little bit, that's going to be cos squared theta, then plus I plus 2I cosine theta sine theta minus sine squared theta. And in terms of real and imaginary parts, if we bring all the things not involving I together, we get cos theta minus sine squared theta. That's the real part of that expression. And the imaginary part will be I times 2 cosine theta sine theta. And so from that, we can easily deduce, since that's supposed to be cos 2 theta plus I sine 2 theta, that this thing here is going to be just cosine 2 theta. And this thing here is going to be sine of 2 theta confirming what we already know. But this is now a very general approach. So let's see what happens if we go up one step. So now let's try n equals 3, a little bit more ambitious, and see if we can get some new formulas. Okay, so let's start with cosine theta plus I sine theta cubed. Okay, let's expand that using the binomial series, binomial theorem. So I remind you, over here is a little Pascal's triangle on the side, just to remind us, okay? So we're going to expand this. All right, so let's go over here. So this is going to be cos cubed of theta, the cube of the first one, plus 3 times the square of the first term times the second term, and then plus 3 times the first term times the square of the second one, I sine theta squared, and plus the second term, I sine theta, all cubed. Okay, we know that I squared is equal to -1, so it allows us to simplify these things. So we can bring all the things involving the 1 or not involving I at the front, so that's the real part. So that'll be cos cubed theta. That will not involve I. This one here will involve I, and this one here will involve I, but this one here will not. And that will be, after we square the I, will become minus 3 cosine theta times sine squared theta. And then the stuff involving I, there will be 2 components. The first one here is 3 cos squared theta times sine of theta. And then when we look at this one here, this last one, I cubed will be I times I squared, which is minus I. So altogether, minus sine cubed theta. Okay, now we know that's supposed to be equal to, maybe I'll write it here, we know that's supposed to be equal to cos 3 theta plus I sine 3 theta. And so we can deduce that this thing here should be cosine 3 theta, and this thing here should be sine of 3 theta. Now, I just want to have a look at this first one. So we can deduce then that cos 3 theta is, I'm going to rewrite this. This is valid expression, but I want to write it a little bit differently because it's nice to get everything just in terms of cosine thetas in this case. So we can do that, of course, by replacing the sine squared with 1 minus cos squared theta. And when we do that, what do we get? We get a total of 4 cos cubed theta minus 3 cos theta. And does that jive with what I said up here? 4 cos cubed theta, whoops, minus 3 cos theta. Yes, I think that's right, okay? So that's a nice expression. And in fact, it turns out to be what's called the third Chebyshev polynomial. So this is an aside. Chebyshev polynomial. That's maybe T3 of x, which is 4x cubed minus 3x. Okay, so it turns out you can do this for any value. You can do not just for 2 or 3, but for higher ones. And you get very interesting and important family of polynomials called Chebyshev polynomials, named after a famous Russian mathematician from the 19th century. Okay, so that's great. So we have now quite a general technology for actually writing cosine n theta or sine n theta in terms of just cosines and sines, cosine theta and sine theta, perhaps with powers. Now another kind of identity is a little bit, did I write one down here like this? No, okay, I'll write down another. So another important identity is this one. Cos squared theta equals 1 plus cos 2 theta all over 2. And correspondingly, sine squared theta equals 1 minus cos 2 theta over 2. Now, why are these important? Well, because they're useful for integration. If you had an integrand and it had a cos squared in it, you might not know how to integrate that. But integrating cosine 2 theta is a lot easier. Okay, so this kind of thing, or this one here, can be used for integration. So how might we establish things like this, or maybe generalization? Suppose we wanted to know what cosine cubed theta is, a corresponding formula for that, or for a sine cubed theta, etc. Well, so I'm going to show you the basic idea. Again, we kind of go back to our basic formulas, the ones right here up at the top. But now we can sort of use these ones here, okay? These ones here. So let's have a look at that. So I recall cos theta equals e to the I theta plus e to the minus I theta all over 2, okay? So let's go back here. So if we wanted to, let's say, find cos cube theta, let me do that one, and hopefully it will be clear. So cosine of theta is e to the I theta plus e to the minus I theta all over 2. So we're cubing all of that. Okay, so we're reducing things to an exponential in this case, and then we are going to, again, exploit the binomial theorem. So maybe the 1 over 2 cubed can come out front, so that'll be 1 over 8. And then we'll expand the rest. So again, it's something cubed. So we get the cube of the first one. E to the I theta cubed will be e to the 3I theta. Okay. And then plus 3 times the square of the first one, which will be e to the 2I theta, times the second one, e to the minus I theta. Maybe I'll go down here. Plus 3 times the first one, e to the I theta, times the square of the second, it's e to the minus 2I theta. And finally, the last one, e to the minus I theta, all cubed. So I'll put a 3 there. I'll do that like this. So minus 3I theta, close bracket. So have a look what we have here. Here we have a combination of exponentials. And the trick is to try to extract various cosines and sines by grouping together appropriate terms. So let me write that like this. So I'm going to take the e to the I3, I'm going to take the e to the 3I theta and the e to the minus 3I theta and put them together. And maybe actually I will make that a quarter so that I can pull a half inside, which you'll see why in a second. So e to the 3I theta plus e to the minus 3I theta, and I'm bringing this 2 inside. Okay, so that accounts for this first and last term. Now, we also have a 3, and these terms here are what? Well, there's e to the 2I theta times e to the minus theta. That's the same as e to the I theta. And this one here is e to the minus I theta. So it's e to the I theta plus e to the minus I theta. Okay? And we've agreed to bring the 2 in, so there's going to be a 2 in there like that. Okay, so what do we get? We get 1/4. And now this thing here we recognize, because that's e of something plus e of minus that something over 2. So that's cosine of 3 theta. And over here, what do we have? We have e to the I theta plus e to the minus I theta over 2. Well, that's just cosine of theta. So we get that cos cubed theta is equal to 1/4 cos 3 theta plus 3 cos theta. Okay, and I'm going to leave the following to you as an exercise, the same kind of thing, to try to calculate sine to the 4th of theta, and I'll give you the start. So what you need to do is to start with e to the I theta minus e to the minus I theta all over 2I, and you can raise that to the 4th power. And you have to just remember the 2I, okay, in the denominator there. Okay, it's not 2, it's 2I. So you'll have to take that into consideration when you do your binomial expansions. And so the exercise is to show this is that what you end up getting is 1/8 of cosine 4 theta minus 1/2 of cosine 2 theta plus 3/8. Okay, that's a good exercise. Okay, so we see it's a rather powerful thing. The idea is that we can kind of exploit the Moivre's theorem, and we can exploit these basic relations. And in fact, this is a philosophy, actually, that is quite a lot more general. So I'll just mention this. It's quite more generally. Most trig identities involving sines, with sine thetas, cos, 3 thetas, tan of theta to the 4th, that kind of expression and various combinations of these things. Most of these identities can be established. By replacing everything with complex exponentials. You might like to think about this. It's a fun thing to think about. So what do I mean here? So let's say you have, cos theta, just to start that, e to the I theta plus e to the minus I theta all over 2. So one way of proceeding was to say, let's let u be e to the I theta. Okay, we'll just let u be this. It's a complex number, typically, on our unit circle, somewhere there. And then we can write this thing as u plus 1 over u all over 2. Okay, so there's cosine theta expressed in terms of u. What about cosine 2 theta? Well, that's going to be e to the 2I theta plus e to the minus 2I theta all over 2. So in terms of u, well, that's going to be u squared plus 1 over u squared all over 2. All right. And what about sine? Well, sine theta is going to be u minus 1 over u all over 2I. And sine squared theta is going to be u squared minus 1 over u squared all over 2, etc. Okay? And once we have the sines and the cosines all in terms of u, well, then you could easily have tans also in terms of u. So if you have some big trig identity, so a big trig identity, which formally might require all kinds of clever thinking. Okay, so a big trig identity actually reduces to just a polynomial or rational function identity in U. Okay. So this sort of basic trick of just employing a single variable for a complex number on the unit circle actually is a very powerful tool to deal very widely with a broad class of trigonometric identities. Okay, so see you soon.